So let's start off with question number 1.
You know the video you got see? Video. Tutorial one. And got your voice, got your pen.
I know.
Okay, so we're given the data paths between some registers and the arithmetic and logic unit, the ALU. So in this particular architecture, we actually have 3 buses. We have 1, 2, 3 buses. Okay, so okay, so in this architecture we have 3 buses, and the question asks us what direction is the data flow. So it asks us to draw some arrows on this diagram showing the direction of the data flow for each of the connections. So for the ALU, let's start off with the ALU. What will be the direction of these data paths here? Okay, these paths are going to be downwards because the ALU will take 2 inputs and give an output. So these must be the inputs, this must be the output. Okay, so those data paths are downwards. What about the path to the registers? These paths here, which direction will they go? Okay, they will go upwards because we want the outputs from the registers to be sent to the ALU so that the ALU can operate on those values, and then the output from the ALU we want to be able to store back in the registers. Okay, so if we draw the arrows on the diagram, it will look like this. From the registers, we can actually output from the registers to either of these 2 buses. Okay, so the advantage here is that we can output from 2 registers at the same time to 2 different buses, and then we have the data paths from these 2 different buses to the inputs of the ALU, and then the outputs of the ALU can go back to the registers. Okay. Any questions on that? I think that's quite easy.
Hard to draw.
Okay, so let's go on. The next part of the question asks us how many clock cycles certain operations will take.
2, 1, and
This one, the first one.
4. First one is 4. Other 1.
So
1 or 2, 1 or 2.
suppose we want to take the contents of register 1, the contents of register 2, add them together and put the value back in register 1. How many clock cycles will that take? Given that we have 3 buses, I'll leave the diagram on the other display, the architecture. We have 3 buses, so how many clock cycles will this take? 1. Okay, so how do we do all of this in 1 clock cycle? Yeah. Okay, so
House.
What cycle? Do you need cycle?
Each bus
fetch two operand. R1 and R2
Then the
together.
clock out, he will come out from here, the clock in.
We have our clock, which looks like this. So the clock has a rising edge and a falling edge. So the rising edge we can call the clock in, the falling edge we can call the clock out. So we can actually output the values of R1 and R2 on the clock out into the accumulator, perform the addition, and then on the clock in we can put that value back in R1.
One cycle, one to two.
Same lah. It's just inverted. Yeah, we are also same.
Wrong,
So
wrong.
um,
I thought I seen
we
one.
can write this as a table
Fight,
where we have the clock and the action. So for each clock cycle, we have the falling edge and the rising edge. For this example, on the falling edge, we can output the values of the register to the accumulator, perform the addition, and then on the rising edge, put the result of the addition back into register 1. Okay? So for this instruction, then we only require one clock cycle.
Excuse me, what clock cycle is from the rising edge to falling edge or falling to rising?
Both way also.
No, one clock
Depending
cycle
on
includes
architecture.
both the rising edge and the falling edge.
Yeah, starts from,
Okay, so no. So actually, you can interpret it either way really, but the clock cycle, I mean, the way we normally write it is that we write the falling edge first and then the rising edge.
Either way also
Okay, so 1A is the falling edge, 1B is the rising edge. And the clock cycle
One cycle is
includes
doing clock in,
both of
the other
those.
clock in. So the
Okay.
clock out will never.
One cycle is rising edge, falling edge.
That one is one clock cycle.
So if you look at each falling edge and rising edge, also same lah.
No different, opposite only. Okay, same lah, no different. Opposite.
Any other questions?
One dot cycle. This one go in. This one.
No, it means that the
Oh, this one is rising edge.
Okay, let's go on
This
to
one
the
is
next
rising
part.
edge.
rising edge this one come down.
Oh, rising edge
Then
come down.
you can opposite also can.
Oh,
Or you
this one.
right or the rising edge you this one go in. You calculate.
Suppose we
Falling
have
edge should come down. One
a
second.
more complicated operation because we have 3 registers in our architecture.
I teach you 4 times I can
We
back.
want to take the value of R1 and the value of R2, add them together, and then add the value of R3 and put the result back in R2.
Can I? What's the answer?
So again, we have 3 buses to do this. How many clock cycles is this going to take? 2? Okay, so again, we can write a table.
Right? You could answer 1, 2, 3, 4.
No lah.
Okay, so the first clock cycle is the same as before. We take output from R1 and R2, send it to the ALU to add, and then clock 1B, put the value back in the register R1, and then the next clock cycle, we can take this value R1, which we've just calculated, and output it on one of the buses. We can output R3 on the other bus, send it to the ALU to add, and the result of that on 2B we can put back in register R2. Okay, so we can complete that operation in 2 clock cycles.
This one I think you say this 4.
Yes?
if I have 4 buses, then I need only 1 clock cycle to finish.
Yeah, I mean, you could design another architecture. So yes, I mean, if you had 4 buses altogether and you had 3 buses here, then in principle you could output R1, R2 and R3 at the same time. But then you would need a more complicated ALU that could take 3 values. So
You first.
you couldn't do it with the same ALU. Okay?
I can hear you.
I mean,
I got 5 bars how? I got 0.5 cycle.
many possible designs.
No, this is very quiet.
Ini
Camera recording ke?
You
Camera recording ke?
can see the I think compares.
No, I never see. He got compared.
Conquer, that's like he like him eh. Con guy, respect. You never see what's that?
You got see Who sabo me
Sure you man.
Maybe not so much sabo me now.
Okay?
Maybe 研发很
Any questions?
未了未了
You want to sabo?
未了個 store 很 smart 啊
Huh?
未了個 store 很 smart 啊
He's huge.
Okay, so now we're given a slightly different architecture. We still have 3 buses, and we have the 3 registers, but we put some registers on the inputs of the ALU. Okay? So the direction of the data paths is the same as before.
I think 這個
You see, no, you come on.
I think 這樣我
And
弄
now we've asked the same question.
一定會有 delay 先
Suppose we have the operation R1.
I think
We want to take R1 and R2, put the value in R1.
Because
For this new architecture
we
now,
store for 1 cycle
where we have the registers A and B, how many clock cycles will that now require? 2. Okay, so in fact putting the registers there means that we have to take more clock cycles
But you can but
because
I need to say one
in the first
we know.
cycle, 1A, we can output the values of the registers, but we can't send them directly to the ALU. 1B, we have to put them into registers A and B. And then the second clock cycle, we can take the outputs from A and B, add them, and then we can put the result back in R1 on 2B. Okay, so introducing those registers, if we have 3 buses, we don't really need those registers. So in fact, introducing those registers doesn't really achieve much because it actually requires more clock cycles to do the calculation. If you didn't have the 3 buses, then you quite often you usually need these registers for the ALU. But if you have 3 buses, you don't really need them.
Most important than
Okay?
the guy have to go to video, take photo, you now here video. Then the white color.
Take picture lah.
Yeah, the picture he have to charge it like go forward.
And then lastly, it's a more complicated operation. How many clock cycles will be required for this one? 4.
2. 1.
Nice one 0.5
Somebody can do it with 3?
I think it's 4.
Somebody can do it with 1. Somebody can do it with 1 millionaire already.
4 they really cannot cannot smart yeah. Cannot just say 4
Again, the first part is to take R1 plus R2 and put the result back in R1. But as we've just seen, that requires 2 clock cycles. Copy out from R1 and R2 to A and B. And then the second cycle, copy out from A and B, add, put the result in R1. When we've done that, we can then copy out from R1 and R3 into A and B, and then copy out from A and B, add the result, and put the result back in R2.
Sir, during the clock 2 cycle, should
wouldn't it be able to run clock 2 and clock 2 cycle at K1 time?
You want to run clock 2 cycle and clock 3 cycle at the same time? Well, the problem there is that you want the value of R1, which is you want the value of R1 plus R2. So you can't, if you output the value of R1 here, it's going to be the old value of R1. It's not going to be the sum of R1 and R2.
Yep, right.
So yes, you could run it at the same time, but you wouldn't have the right value of R1.
Data has it.
Really?
Sorry?
Data has it.
Cannot travel same frequency.
Yeah. Yeah, you could have a different architecture and
Keep
do it, but
keep talking
with
about
this
all the
with this
different
particular
architecture.
architecture,
Of course,
I
right.
think
Then that one is your structure higher.
This is the question.
You see, quite long, right?
Okay, I keep quiet.
This time when I open company, cannot come on. Quite long.
okay.
You can't do expert pipeline. How many stages of pipeline exist in this stage, in this setup?
Let's play the guessing game.
And then the question asks us how many stages in this pipeline are there? So what's the answer here? 2. Okay, because
One set of register only.
Yeah, separately.
because we have these registers for the ALU input, then we call it a 2-stage
But you can clock
pipeline
faster.
because we require the two
Mine
cycles.
So actually 放那个 register 是比较快的。
Can use data for in this.
Can. But got hazard. Yeah. Unless you the ALU go back
ALU back.
那个 ALU output 如果有一个
Okay, so that's question number
wire
one.
再回
Any
去那个
questions
input，
on question number
可以
one?
用
那个有点像 sensor，可以 feedback。
一模一样，一模一样。
不需要啦，just 你 just output of the data 那个 ALU，just data forward to the next clock cycle 就可以了啦。
data forward 啦，
这边而已嘛，
ALU 来 ALU 啊。
不需要回去
Because
then 下来
the first stage is from the registers to the first stage is from the R1, R2, R3 registers to the A and B register, and then the second stage is from the A and B register to the ALU operation,
R1 plus R2 是一
and
个
then back
flow嘛
to
then after that R1 plus R2 plus R3 是另外一个 flow 嘛 then 你可以 data forward 出来。
every operation
But in
requires
the
two
real life
cycles.
implementation,
Requires
it's
at
go
least 2
back.
Ah, the
cycles.
real to the. It's quite long, right?
What shit？
You see, quite long here. 好，最好放反正去。
Extra. What? They say A and B to ALU ah?
Where's the camera?
Okay, so question number 2 then asks us what the maximum operating frequency is for
Here
the
is 1.
clock,
Here is 1.
and it gives us some
Below is 2.
values.
Basically the register
It says that
separates.
the signal
one,
propagation
then
delay
below
from the
here is
register to the ALU from its input
register like
registers
divider.
is 200 nanoseconds, and the signal propagation delay from the ALU output back to the registers is 2 nanoseconds. Addition and subtraction take 50 nanoseconds, multiplication and division take 200 nanoseconds, logical operation takes 25 nanoseconds.
Boring this kind of question.
Yeah. Okay.
So it asks us to do this for both the architectures. So for the first architecture, where we have the 3 data buses but no A-B registers, what would be the maximum operating frequency of the clock? Can anybody work that out?
200
One.
plus 200.
Okay, 1 divided by 600. Yeah, 1 divided by 600 nanoseconds. Okay, that's correct. How do we get that? Well,
Because the input
for
to
the
400,
first
the output is
architecture,
200, so it's 600. So 1 divided by 600
we
equal to 400.
can complete all of these
Two
in
into
one
one,
clock
two into
cycle.
one is 200. It's 200
So
plus
in the
200
first
is 200.
architecture,
Then after that, output is 200. It's total 600.
we can propagate the signal from the
1
registers to
divided by
the ALU.
450
We
lah.
can carry out the
Loop by then.
operation in the
It's one
ALU, and we can propagate the
Input
signal
是
back from the
input 是
ALU
200
to the
嘛
registers.
回去200
output 是200嘛
addition 50
So what value do we use for the operation? Well, if you want to calculate the maximum operating frequency, you have to take the longest operation, because
What's the
the
longest?
frequency has to be able to cope with all of these operations. So
So
you take
错啦。
the longest in order to
Divide.
calculate the maximum operating frequency.
Yeah, that's true. That's very true.
Okay, so the
Yeah, the biggest-
maximum
because the biggest can cover
ALU
everything.
operation,
Yeah.
or maximum ALU delay, is 200 nanoseconds. So therefore, for this architecture, the total delay is 200 from the registers to the ALU, 200 ALU delay, and 200 from the ALU back to the registers, which is 600 nanoseconds. So the maximum frequency we can operate at is going to be 1/600, or 1.67 megahertz. Okay, any questions on that?
600 is what the input.
The input is 200, the output is 200. Then after that,
Normal?
ELU, right? Maximum because it's 200.
Determined by maximum.
So it's total 700.
Yep.
Even though it's maximum operating frequency, you need to guarantee all the instruction can be run in the situation.
Yes, yes. The question really wants the maximum operating frequency.
Shortcut lah.
We have to be able to handle all of the instructions. Okay?
Round trip.
Round trip means
Any other questions?
through and fro.
Yep.
200, 200.
200, 200.
I use that. Yeah. Round trip.
I think that's the same question as
That's for me to understand.
I've just been asked over there. Yeah, what the question wants really
From down
is
here
the maximum
is 200,
frequency
then
at
go
which
back
you
200,
could operate
then ALU
and
is
still be able to handle all
200.
of the different operations.
True BD.
So if you took the minimum operation,
Yeah.
then you wouldn't be able to handle
Then you cannot do divide.
the division. Okay, I mean if you took 25 nanoseconds as the ALU delay, then yes, you could handle logical operations, but you wouldn't be able to handle division, you won't be able to handle addition and subtraction. So if you want to be able to perform all of those operations, then you need to get maximum operation.
Yeah, but that's the minimum frequency that the needs to operate at. It's not the maximum frequency.
Well, yeah, no, I mean it is the maximum, because you could operate at below 1.67. You could operate below this frequency and still be able to carry out all of these operations.
Then you got the wrong
But if you operated above this
frequency
frequency,
is
then
higher
you
than
wouldn't be able
Take
to
the
do
longest one,
all of this
time
in
is
one
walk
clock
the other way around.
Because
Okay,
the frequency
you,
is higher,
you,
right? He can
the
have more.
one
But
clock cycle has to
frequency
be at least 600
He maximum
nanoseconds.
frequency can
So that's
up to
a minimum
1.67,
time
but
for the
lower
clock
he can still can
cycle,
operate
but
everything.
it's a maximum time for the frequency. Okay, so that's for the frequency and the maximum frequency. Okay?
Why is it 1 divided by? Why must
Lower
it
frequency.
Frequency mah.
always standard?
One divided by the time.
Okay, so for the first architecture we have 1.67 megahertz.
I think when you hear this video, I think me and Kenneth probably said.
What if we go on to our second architecture, where we now have these A and B registers? What is going to be the maximum operating frequency for this?
Who's that? 200
Anybody
plus
tell me?
200 plus 200.
times 2 or
加2
Okay.
还有两个 A B 嘛
1 divided by, what do you say? 400. Okay, yes.
This one is what? This one is what?
B 啊 B 是 B 啊
Given the
So for this architecture,
B.
we said it was a two-stage pipeline. So in fact, it takes 2 clock cycles,
because
and
the
the
longest
first
is 400.
stage is from the registers
600
to,
divided to
well, from the registers R1, R2, R3 to A and B, and that has a delay of 200 nanoseconds. And then for the stage 2, from the, which includes the ALU delay and the signal propagation from the ALU back to the registers R1 and R2, that's 200 plus 200, which is 400
Take the maximum
nanoseconds. So it's a 2-stage pipeline. The first cycle has to be at least 200 nanoseconds.
这个是400
The second cycle has to be at least 400 nanoseconds.
very clever
So
I suspect the call is quite
overall, the clock cycle must be at least 400 nanoseconds, the larger of these two. So if we take the maximum operating frequency, the maximum frequency is 1 over 400 nanoseconds, or 2.5 megahertz. Okay, is that clear?
Then for register AB to ALU, there's no delay.
No. According to the questions, there's no delay. You can ignore it. Because, I mean, A and B are the input register, A and B are the input registers to the ALU. So the signal propagation delay is going to be very small, therefore it can be ignored.
So this is the stage 1 and stage 2.
Okay, so
Cycle lah.
Huh? Wait,
we have 2 stages.
2 stages.
Have to work out the
again.
time, the delay
This one's
for
200.
both stages.
And this
Take
one's
the
200.
take the larger,
Wait,
and that gives
Because
us the operating frequency.
499.
got take digital system. Got take digital system. Digital system you will learn one.
Is it?
Yeah. Basically, one pipeline, when you divide the whole circuit, then you will divide the pipeline divide into 200 and 400, right? The 600, right?
不要这样跟他讲，这样 very messy. These two is the A and B, right? A and B register going right. Then at this, you just imagine these two separate. Then he got two. I think one more.
Okay, everybody happy with that?
1, 2, yeah. So this one is another one is the ALU delay. ALU,
So,
I think it's AL.
let's go on.
Each one is also AB. You have to store back AB again. And down here, right, is the ALU. So this, at this cycle, right, you take 200.
200.
At this cycle, you take 200. So in order to have the maximum frequency, right, you take the highest one,
The long.
which is this one. So it's 400. That's it.
So
Bacteria.
here we're given a single bus architecture, and we have various registers. The program counter, the instruction register, the memory address registers, the memory data registers,
You got take DSD one
ALU,
digital system design.
So on.
So now Fahmi teaching. He will teach after that.
and we're told
After that you will understand what it means. Don't worry.
Don't know that you can ask.
We-
Ask why.
have to write
After that he will
the
teach why it's take for.
control sequence for this particular operation. So what this particular operation does is to take the memory location M1, which is part of the instruction itself. The M1 is specified in the instruction.
Not like you were teacher.
We want to take the contents of that memory location M1 and load it into the register R2. And we're told that we can assume that the program counter initially.
Or battery weak.
Sorry.
You see?
I think yesterday computer no better. Who got adapter or who got laptop?
And then yesterday our teacher come inside, right, 10 minutes his laptop no battery. Then he asked, anyone got laptop and lend me? Then no one.
Yeah, after he thought microphone cannot hear. Then button cannot click.
Okay, we're told that the program counter initially points to the instruction.
So program counter.
Sekali ni boleh record lah.
Got record lah, red colour.
Record solo sekali never record.
Then Rafi die lah.
Then after we record cannot, he reteach everything. Then we should cannot stop.
Yeah.
这个我有点 blur， 也是 every question a bit blur。
它 sequence to load 嘛，对不对？ So program counter go inside.
Okay,
Instruction.
before I go through the answer, can anybody tell me how many clock cycles this takes?
Program counter go to instruction register. Instruction register to decoder. Then decoder go to memory address. Memory address.
2 吗？
Well, we have to go to external memory.
Memory address.
I think it's 2.
Take the memory
Okay.
address and store
What's answer? What's answer?
4.
4 吗？
Load PC,
Load only 吗？ Only ALU 吗？
external to
Program counter. Go to instruction register. Instruction register to decoder. Decoder to memory address. Then for memory data come back in 4. Go back into register. No need to use ALU because got no app.
But you will use back the register thing or not? You have to store back to load R2 got.
Okay, so
6.
it's not quite so simple. But let's go
Because
through
you
it
have to
in
go to
detail.
the register also. You just say 4, right? I say 2 more. 4 plus 2 to the 6.
okay lah, get the idea.
It's something like that. Something like that. It's not. It's 1 bus. So
Yeah,
you
1 bus.
Okay, so you have the answer on the display here. So let's go through the answer and see what is happening. Okay, so first of all, we have our program counter which points to the current instruction. In order to get that instruction, we have to get the output from the program counter. So in clock 1A, we can out from the program counter. We want to do 2 things with this. We want to get the instruction that's pointed out by the program counter, and we also want to add a value to the program counter for the next instruction.
no app, man.
Okay, so
The next one instruction.
we
You got the S. It's 21 clock cycle.
we output from the program counter and we
Want to
select a
send
constant
in
here
to ALU.
so that the
Cycle to select that
ALU
too.
can
Because
add
1
the
bus only.
value to the
开的时候它
program
自己
counter.
AL，
And then
它
from
它会
1B,
变成 AL。
the
因为有一个 hit
value of the program counter, which is the address of the instruction, is input to the memory address register because we have to be able to access the external memory. And also in 1B, we can add together the constant and the previous value of the PC and put that into the register ACC. then in 2A, we can output the value of the memory address register, and we can read that address from external memory, and at the same time we can output from the register ACC.
We are using which bus? The one between PC to MAR or through the single bus?
Okay, no, these are the data paths. I think these are just the
You never see
control
the single
signals.
DF, you never
Okay?
see a single bus.
So we're using the data paths, yeah. Okay. Okay, so, and then we have 2B, which takes, so we've already read, we've sent the address to memory, external memory, and we've read the value, so that value will come back from external memory and input into MDR. Okay? And also in 2B, we can take the value we obtained by adding the constant to the PC, and that value can go back to the PC register. Okay, step 3A now, we have a value in the MDR register, we can output that, and in 3B we can input that value, which is the instruction, to the instruction register.
Whether you do the decoding?
4A, we can output from the instruction register,
Copy everything.
and we can output the address M1.
After you then you stop it to
4B, that address M1 gets sent to the memory address register.
then go down.
5A, we output that address to the external memory again. We read from that external memory. 5B, we input the value of that external memory into MDR.
MDR go to register.
6A, output from MDR,
Go to register.
and store the value 6B in register R2. Okay, so it's more complicated because we have to read from external memory, and when we read from external memory, first of all we have to send an address out through the memory address register, read the value from memory, then get the value back through the MDR, the memory data register. Okay, so this all takes clock cycles.
I think exam will come up.
This question confirm got one.
Normally exam
you have
question
to
accept
write
one.
control sequence.
Yeah, confirm got this one. I think but I think much more complicated. I think he'll come out two their bus.
Exam tips from Mike. Exam tips from
Okay,
Mike.
any
I think
questions
this one
on
will,
that?
will come out. Only not
Too easy.
Yeah, too easy.
Sub question.
Even the lecture topic is your accumulator. Accumulator resistor.
Okay, let's go on then to the last question.
Last question. Wow.
Okay, so
This one is the raw, the WAW.
What raw?
In into
Read after right, this sort of thing. So data
sorry,
has
I forgot to hand round the attendance sheet. Can you sign that
It's
while
got
I
to
go
be
through the last question?
so confusing.
Okay, so the last
sweet,
question is
How many
about
step this is?
instruction level parallelism. So here we have a pipeline where we can overlap the execution or overlap different instructions. So an instruction goes through various stages. We have to fetch the instruction, we have to decode the instruction, we have to execute the instruction, we have to operate in the memory and so on, and write back the value. So these can be executed as a pipeline.
See? 看后面从
So
这全部是对的。 上面有没有
Question gives us some example code. When we're executing these instructions in the pipeline, because we're starting to execute one instruction before we've finished executing the previous instruction, we can have what we call hazards. So if there's a data dependency between two instructions, for example, one instruction may write a value to a register, another instruction may read that same value from the register, but if we start to execute the second instruction before we finish the first instruction, we may get the wrong value of the register. Okay, so we're given an example and we're asked to identify all of the data dependencies, and then one way of resolving these data dependencies is by using what is called stalling. So we're asked how many stalls are required.
3 No data forwarding. Can swap or not? Cannot, right?
不可以，你说的 very strong。
Cannot swap at all, right?
Cannot swap.
So 3 stall, I think.
What is store? Chicken rice store, Western and more.
Okay, so
I think 3 stalls. I think.
You think? I thought you confirm.
okay, so we're given one example of a data dependency. Here we have a register R0. This instruction adds R1 and 100 and puts the result in R0, and the next instruction uses R0 to load a word into R2. So here we have a data dependency. If we start to execute this instruction before we finish this one,
1, 2,
we may
3, 4.
get the wrong
Yes,
result.
4.
So can you identify other data dependencies? What are the registers?
R2.
R2, between which instructions?
Between load and add.
Okay, so here we have another data dependency. We load the value of R2. We calculate the value of R2 here, and we need the value of R2 for this next instruction. Any more?
I think 8. I don't know.
I think it's only 4. Too much already.
R2, we've just looked at R2, yes. Other ones? R3, between which instructions?
Switch and on. Store and add. Hey, store. Hey, store.
Okay, here this add calculates the value of R3, and we use it to store that value into this address, and we also use R3 down here for the OR instruction. And what about R0? Are there dependencies involving R0? Okay, so again, we use R0 here,
Oh, yeah.
so we have another dependency involving R0.
I thought you use anything.
9.
Can say a number. Huh? You don't know, man.
R5 where?
9 dependency. 9 stalls.
Okay, so
Full connection here.
this is this is writing a value to R5, and this is also writing a value to
I'll probably
R5.
flunk like that.
Um,
I heard nice.
You're right in that sometimes there's also a problem with right after right dependencies. But this is not a true data dependency, but on some architectures it can cause a problem, because if you write after write, and you do that concurrently, it is possible you might get the wrong answer. But it's, I think the question asks for the data dependency, so it's not really a data dependency. Okay, it's right after right.
So you read after right is actually that.
I think nice. I think nice.
What did the question actually say?
Sorry lah.
I think in this case it only wants the read after write. Not for this question. But, yeah.
Well done.
Okay, so we can draw a new diagram.
The minute I see, I know already.
Got stickman again ah.
Where you?
Oh, maybe stickman.
Insert the D, you right? Headband.
Okay, so if we draw the arrows to indicate the dependencies,
Headband.
then when we write the value of R0 here, we have a dependency because we use that value of R0 in the next instruction, and we also use the value of R0 here in the store word, and we also use the value of R0 here in the last instruction. When we calculate the value of R2 in this instruction, we use it in the next instruction. Here we calculate the value of R3, and we use it in the next instruction. And also the value of R3 is used in the last instruction.
For the store is read also. No, but read.
The store is a read because you're storing the value of the word into this address.
Both are read. R0 is read, R3 is read.
Okay, because as far as the registers are concerned, yes, because you're storing into a memory location. You're not altering a register. You're just storing into a memory location. So, in order to perform this operation, you take the current value of R3 and the current value of R0. So both those registers are read.
Is E man or A man? FDAM.
Okay, so those are all the read after write data dependencies.
This one wrong.
We can see that this could cause us problems because in instruction 2, you want to use the value of R0 before you've actually calculated the value of R0 in instruction 1. And similarly, in instruction 3, you want to use the value of R2 before you finish calculating the value of R2 in instruction 2. So if we just try to execute these instructions like this, we will get the wrong result, okay? Because we will not use the correct value of R0 in instruction 2. We will not use the correct value of R2 in instruction 3. So we have to put in some stalls. Using stalls is one way of resolving this problem. So for this particular example, how many stalls would we need in total to resolve all the difficulties?
I don't know, I think
How many? 9?
NOP.
Okay, let's see.
What?
Huh?
Well, I say 6.
I say 9.
I just playing the guessing game.
Sorry?
Instruction will be fetch R5.
Think 5.
Instruction.
4. Anybody 4?
For my analysis, for my analysis is 9.
command should be any real number, real integer,
Okay,
any
yeah, I
real
mean,
integer
for this
that is
example,
more
the
than
right
0,
answer, right,
and that's the
doesn't matter
infinity.
Because
Then after that, discriminate your answer.
You get the mark there.
here
Your answer, you got it's not wrong, right? Yeah.
At
least you got some accurate number. Give a range. At least you got something.
Okay, so although there is a right answer, for this particular pipeline, the right answer, right dependency does not cause a problem. Okay.
Link file.
Why 9?
Okay, so
The first two instruction got 6 already.
The what?
The first two instruction got 6 already.
First two instructions.
see how many stores we have to add.
The first two instruction got 6 already.
Okay, so we had a dependency between the first instruction and the second instruction. So we have to insert 3 stores so that we don't use the value of R0. We don't try to use the value of R0 before it's ready. Here we have another data dependency between instruction 2 and instruction 3. Again, we need to insert 3 stores so we don't try to use the value of
You see that S
R2
2, 3, 4, 5,
before it's ready.
He just put 3 stores, the data out already. Right?
Here again, we have a dependency between the third instruction and the fourth instruction. Again, we need to insert 3 stalls,
Can I never tell?
so we don't lose this value, which
One special unit,
is
5,
R,
F, D, E, M.
R3 before it's ready.
So you asking for
How many stores?
This data dependency here between R3 and the final instruction,
your whole thing will
for that-
have no problem, no hassle.
for that case, we don't need to insert any stalls because
data really is ready.
we won't try to write this instruction, we won't try to execute or use the value of R3 before it's ready.
Kind of smart.
But in total, in order to solve all of these problems, we have to insert
the
9
last lecture
stalls
she teaching
in.
I thought NOP is a store thing now.
NOP 也是一样啊。
NOP 是在这边吗 Then
NOP is same as store.
then store 它放在这边。
Okay, any questions on that? What happened to the attendance sheet? Okay. Next week, next Tuesday is Chinese New Year, so there won't be a tutorial. There won't be a tutorial next Tuesday.
Go to his house. You don't use that
I'm not
LSS.
quite sure the best way of solving this. It's a large group, and finding a time when you're all free might not be so easy. Sorry? We send e-learning week. Well, that's one possible. Are the lectures running in e-learning week or not? No. Okay. So, I guess I could catch up in e-learning.
Because for this instruction, right, to be able to use this thing, right, the first instruction is this thing, right, the add formula. So in order for your second instruction to have the R0 value, right, you need to have 5 stores so that you need to have 3 stores in order the data will be ready to use the R0.
the D is the data.
D is the code. Because until this cycle, right, your R0 will be ready. That's why you need 3 stores so that your next cycle, this instruction down here, right, yes, correct. So you can do this one. Then this one there's no dependency because R2 is ready already. So over at this instruction, right, you need to do R3 ma. You need to do R3. So you need you need R2, sorry. Down here you need R2. So down here, right, you need another 3 stores so that this R2 will be ready. Then the next one, right, you'll be using R3. Then you need another 3 more. So that down here below will be ready.
Oh, then this one is all ready.
So are all ready. So this one you need to have.
When in R3,
That's why your R3 down here.
Oh yeah, here is one clock cycle. Actually, this answer wrong.
为什么 actually 不需要 because down here you store
You
everything
write the same,
already.
yeah.
Same ah.
But I teach you what is correct. Don't worry, it's correct.